Section D, two factoring shortcuts. Kinda.
Here's a pattern for you for binomial squares. In a trinomial version of each equation, if the c, or final constant, is a perfect square, and the a coefficient is 1, then take the square root of c and double it. If the square root of c times 2 equals the b coefficient of x, then you know it's a single root equation. For example, you can see that 9 is a perfect square. The square root of 9 is 3, and 3 times 2 is 6. So you know that equation has only one root.
Also, you would recognize 100 as a perfect square. Its square root, 10, doubles to 20. So x squared plus 20x plus 100 fits this same squaring pattern. And you know it has only one single root. This trinomial has the same pattern. X squared plus 10x plus 25. The final constant is a perfect square. It is 25. Take the square root of that amount, 5, and double it. The result is 10, which is the b coefficient. That tells us that x squared plus 10x plus 25 factors into two identical parts, and even tells us what the parts are. The constant term for each part is 5, what we squared to find 25. So x squared plus 10x plus 25 equals x plus 5 times x plus 5. The equation x squared plus 10x plus 25 equals 0 has just one root. X equals -5. There are many patterns that can help reveal special kinds of factors. The best way to discover these patterns is to do many factoring and foiling problems.
Here is one more handy pattern that will let you factor equations more easily if you can recognize it. When there is no x term, that is, no middle or b coefficient term, and when the other two coefficients are both perfect squares like 49 or 25, there's a simple pattern to the factors. Check out this example. X squared minus 49 equals x plus 7 times x minus 7. You can FOIL the check. X plus 7 times x minus 7 yields x squared plus 7x minus 7x minus 49. Notice how the 7x terms effectively cancel each other out, and how the final constant is always a negative perfect square.
In other examples, x squared minus 36 is x plus 6 times x minus 6. X squared minus 1 is x plus 1 times x minus 1. And 4x squared minus 9 equals 2x plus 3 times 2x minus 3. In each case, the two factors look the same, except that one has a plus sign and the other a minus sign between the terms. The first values are both equal to the square root of the coefficient of x squared. The last values are each the square root of the last constant. All you need to do is put a plus between them in one factor and a minus in the other.
Let's take the equation y equals 16x squared minus 100. If you had to factor this and find the roots, this pattern makes it easy. You want to find the roots, or x-intercepts. Following the pattern, you can see that 16x squared and 100 are both perfect squares, with square roots of 4x and 10. So you first factor 16x squared minus 100 into 4x minus 10 and 4x plus 10. That makes the equation y equals 4x minus 10 times 4x plus 10. Now set y to 0 since we want to find the roots. 4x minus 10 times 4x plus 10 equals 0. Finally, set each factor equal to 0 and solve for x. The results are x equals 10 over 4 and x equals negative 10 over 4. Simplify to 5 over 2, and you're done.
The most important way to factor, though, is by trial and error, even if it's a kind of a pain. And if that kind of factoring doesn't work, well, then you can always resort to the quadratic formula.
Section E, the quadratic formula.
As we said, it is not always practical or possible to factor an equation, but it is always possible to find the roots of a quadratic equation by the use of another method, the quadratic formula.
We were determined to stay on course behind Wienerkraft and the X, but we came to a problem we just couldn't solve. No matter how much we tried and erred, we couldn't factor it. We didn't know what route to take.
Remember, we found a formula for the root of a linear equation to be negative b divided by m. In the case of quadratic equations, the root-finding formula is, well, somewhat more complicated. The quadratic formula is x equals negative b plus or minus the square root of the quantity b squared minus 4ac, all divided by 2a.
Yeah, it looks nasty, but don't stress. It's a cakewalk.
By plugging in the values of the coefficients for a, b, and c, you can always come up with the roots of the quadratic equation. Again, using this method of quadratic magic, you may find 2, 1, or 0 real roots.
Okay, now for the rest of the quadratic formula. Remember the equation we failed to factor before? It was x squared plus 5x plus 3. Well, now we can factor it. You can always use the quadratic formula to find roots of equations that you can't factor any other way.
Here's how to use the quadratic formula to find roots. In our equation, a equals 1, b equals 5, and c equals 3. Now, to make things a little easier, before we substitute all these into the quadratic formula, let's just compute the part inside the square root. b squared minus 4ac, which equals 5 squared, minus 4 times 1 times 3, which equals 25 minus 12, which equals 13.
The rest of the formula is now easier to manage. We have x equals negative 5 plus or minus radical 13 over 2. Of course, that is really two answers. Using the plus part of the plus or minus sign, it is negative 5 plus radical 13 over 2. And using the minus part, we get negative 5 minus radical 13 over 2.
Radical, dude!
These cannot be expressed exactly as a decimal or fractional form. If you want to, you can compute accurate decimal approximations with a calculator. If you do, remember to add or subtract radical 13 from negative 5 first, and then divide that result by 2. Rounding to 6 decimal places, we get x equals negative 4.302776 and x equals negative 0.697224. But normally, you can just leave the answers in radical form.
So the quadratic formula helps you solve those equations you just can't factor any other way.
Oh, and by the way, these roots can now be used to factor the original equation. As we saw, if you know a root, then x minus that root is a factor. In this case, we have as an approximation x squared plus 5x plus 3 equals x plus 4.302776 times x plus 0.697224. The only way to give an exact factorization is to leave the square root of 13 in a symbolic form in the answer. X minus negative 5 plus radical 13 over 2 times x minus negative 5 minus radical 13 over 2. You can see why factoring this equation by the trial and error methods used earlier is sort of impractical.
The discriminant is the name for the part of the quadratic equation under the square root, b squared minus 4ac.
In the example we just did, the discriminant was 13. The discriminant is so called because it lets us discriminate with some at-a-glance insight between quadratics with 0, 1, or 2 real roots. After you substitute the values of a, b, and c into the quadratic formula,
I've found the discriminant.
If the value of the discriminant is positive, then there are two real roots to the equation. If the value is 0, then there is one real root. And if the value of the discriminant is negative, then you know immediately that there are no real roots to the quadratic equation.
So remember, if the discriminant is positive, then the quadratic equation will have two real roots. If it is 0, then there is only one real root. And if the discriminant is a negative value, then there are no real roots. Much like me, I'm often considered a negative person, and I moved around a lot growing up, so I have no real roots.
These generalizations are possible because the quadratic formula takes the square root of the discriminant. A square root of any positive number, you'll remember, yields two answers, one positive and one negative. And the square root of 0 yields one answer, since the only number times itself that will equal 0 is 0.
Wait. If the square root of a positive number gives two real answers, and the square root of 0 gives one real answer, which is 0, then what do you get when you take the square root of a negative number?
Ah, yes, square roots of negative numbers. What is the square root of a negative number? Well, the problem we run into here is the inconvenient fact that no real number multiplied by itself will ever give you a negative number. Never, not ever. So, what can you do when your discriminant is negative and you have to take its square root? Well, let me formally introduce imaginary numbers.
Section F. Imaginary and complex numbers.
To represent imaginary numbers, mathematicians use the number or symbol I. I is defined as the square root of -1 or -1 to the 1/2 power. Another way of saying this is that I squared equals -1.
Remember, Earthlings, even though it's a letter, I is not a variable. Also, it's not a real number. It cannot be found anywhere on the number line. It exists only in the mathematical mind. But it is very useful to you all the same.
I can be used to make other numbers with negative squares.
For example, 3i squared equals 3i times 3i equals 9 times I squared equals -9. Similarly, 4i squared equals -16. 5i squared equals -25. You get the idea. And just as the equation I squared equals -1 can be expressed in the form I equals the square root of -1, the equation 3i squared equals -9 can be written 3i equals the square root of -9. Similarly, the square root of -16 equals 4i. The square root of -25 equals 5i. The square root of -36 equals 6i. The square root of... And you get the idea.
Now please listen to me, my little chicken muffins. The general rule is this: to take the square root of a negative number, throw away the negative sign like the devil, and take a square root in the usual way, then multiply the answer by I.
Don't forget, the most important thing to remember here is the square root of -1 equals I.
Howdy-ho, ladies and gentlemen, I'm Red Cardinal. Little reminder for you. Now, don't confuse the square root of a negative number with the negative square root of a positive number. I mean, remember that any positive real number has two potential square roots, one positive and one negative. This means that 16, could have square roots of plus or minus 4, and the negative square root of 16 is -4, but the square root of -16 is 4 times the imaginary square root of -1, or 4i.
Now that you have been initiated into the world of imaginary numbers, you can see how all numbers are of 3 basic types. Real numbers, which are the basic numbers you know and love so well, imaginary numbers, your new and abstract friends, and complex numbers, a deadly mutant hybrid. No, just a combination of real and imaginary.
For example, 3 plus 4i, 1/2 minus 2/3 I, and 0.7 plus 1.3i are all complex numbers. A purely real number, one with no I part, can be written in a complex form as follows. write 7.2 in the form 7.2 plus 0i. Now, why write anything in a more complex form? Well, sometimes you might have to combine a real number with a complex number. Similarly, a purely imaginary number, one in the form 12i, can be put in the complex form 0 plus 12i. This shows that all three types, real, imaginary, and combinations, can all be part of the form a plus bi. Anything in that form is called complex. If b equals 0, a plus bi is a purely real complex number. If a equals 0, a plus bi is a purely imaginary complex number.
Roots of quadratic equations found using the quadratic formula may be real, imaginary, or a complex form that combines real and imaginary.
Section G, a practical example.
One of the most common applications of quadratic equations in the real world is finding the speed of falling objects. Here's an example.
There's a special equation that models the position of falling objects in relation to time. This equation is y equals -1/2 times g times x squared plus vx plus h. First, let's define the variables and constants we're using. The constants in this equation are g, v, and h. The value g stands for the acceleration of gravity.
No matter where you are on the surface of the Earth, the acceleration of gravity is a constant at 9.8 meters, or the American equivalent, 32 feet per second squared.
The squared part happens this way. Speed is measured in meters per second. Acceleration tells how speed changes. If speed gets faster by 9.8 meters per second every second, then you get 9.8 meters per second per second. This constant will be the same in every equation like this for Earth's gravity. The value v stands for initial velocity. Initial velocity is the velocity of the object when its position is first measured. That is, when time, the x variable, still equals 0. Finally, h stands for the initial height. The initial height is the height of the object when its position is first measured. The dependent variable y stands for the height in relation to the independent variable x, the time that has passed.
For our example, Galileo Galilei stands on the edge of a 122.5 meter high cliff with a bowling ball. He drops it off the edge. How long will it take the bowling ball to hit the ground below? Using the function we know, between the position of a falling object and time, y equals -1/2 times g times x squared plus vx plus h. We can now answer this question. First, we must identify the constants. The height we are dealing with is measured in meters, so the value for g we use is 9.8 meters per second squared. Galileo doesn't throw the bowling ball, he simply drops it. So the initial velocity, v, is 0 meters per second. And since the ball is dropped from a height of 122.5 meters, the initial height, or h, is 122.5 meters. Plugging these values into the equation, we get y equals -1/2 times g, 9.8, times x squared plus v, 0, times x plus h, 122.5. This simplifies to y equals -4.9x squared plus 122.5.
Now, the variable y represents the height of the ball in relation to time x. We want to know how long it'll take until the ball hits the ground, which is where the height y equals 0. So, we must find the time x when the height y is 0. To find x when y equals 0... Wait a minute, that's a root! In effect, we want to find the roots of the quadratic equation. Y equals -4.9x squared plus 122.5. There are a couple of different ways we can do this, and one, as we just discussed, is by using the quadratic formula.
In this quadratic equation, the coefficients are a equals -4.9, b equals 0, and c equals 122.5. We can plug these values into the quadratic formula in order to find the roots of the equation. This will give us x equals -0 plus or minus the square root of the quantity 0 squared minus 4 times negative 4.9 times 122.5 all over 2 times negative 4.9, which equals x equals plus or minus the square root of the quantity negative 4 times negative 4.9 times 122.5 all over negative 9.8, which equals x equals plus or minus radical 2,401 over negative 9.8, which equals x equals plus or minus 49 divided by 9.8, which equals x equals plus or minus 5. The value of x cannot be negative because Galileo drops the ball at time x equals 0. So x equals negative 5 would mean 5 seconds before he drops the ball. It's illogical. So the bowling ball hits the ground 5 seconds after it's dropped.